Hi, we're going to talk about thermodynamics. This corresponds to B4 and IB. So specifically, we're going to cover the first law of thermodynamics, and then all the different processes that we can do to an ideal gas, and then we're going to cover entropy and the heat engines and the Carnot engine. So before any of this, there are two big laws that you should know. Um, as well as one small fact. So the first is the ideal gas law, PV equals nRT. This is pressure, this is volume, this is number of moles, and this is the gas constant, and this is temperature. Where R is equal to this right over here. So alternatively, you can also write this as, nkt, where n is the number of particles. So we would notice that actually n is equal to small n times Avogadro's number. And k is the Boltzmann constant, which is 1.38 times 10 to the negative 23 joules joules over Kelvin. So this is the ideal gas law. Usually we just use the first one because moles is just easier to use, but this is also sometimes useful. The other thing is the first law of thermodynamics. So the first law of thermodynamics states that Q equals delta U plus W, or my favorite version is delta U equals Q minus W. Now, U is internal energy. U is the internal energy of a gas, and that consists of all the kinetic energies and potential energies of the gas. But for the sake of ideal gases, this PE part is eliminated. So we only care about its kinetic energy, and we know that the kinetic energy of an ideal gas is 3 over 2 nRT, or 3 over 2 nkt. And so we would find that the internal energy of a gas is a unique function of T, because once you're given the number of moles or number of particles of a gas, the only thing that you can change in a closed system is the temperature. So if you want to increase U, all you have to do is increase the temperature. Now, this is the beauty of this version. If you think about trying to increase the temperature of a gas, there are two intuitive ways to do it. The first way is by heating it. So you're going to get fire, and you're going to heat up the container of gas. Then you would find that Q is positive, and we first don't care about W. Then delta U would be positive, or like if W is 0. So the first way is by giving a heat input. So that's what we mean by Q. Q is equal to heat input. Heat input. We directly transfer heat into the system. Now, the other way to do this is by making the volume smaller. So if you think about if you have trapped gas inside a piston like this, then by pushing down the piston, you can increase the temperature. And that basically means doing work on the system, or basically the work done by the system is negative. So basically the gas pushes against the force like this, but the actual displacement goes downwards. So this work here means work done by the system or by the gas. So these are the two ways in which you can add or take away from the internal energy of a gas. And together we have this first law of thermodynamics. Now, at root, this is just energy conservation, because it's trying to say that all the changes in my internal energy can be accounted for by some energy input or some energy output, or their combination. So this is a very important prerequisite before we look at PV diagrams. So now we're going to examine exactly this model right over here. So we have this container, and we have a piston that seals it tight into a closed system. And inside we have a lot of different particles that move around, right? So that's fundamentally, we're going to assume an ideal gas. Now, to describe this system, we have mainly a couple variables. We have P, we have V, and we have T. And the relation of these variables is already examined in the ideal gas law, right? And what we're going to do is we're going to draw a diagram that shows the state of this system. And we're going to draw a VP diagram. This is something very conventional. And now you might ask, why do we not draw T in? But then remember, this is an ideal gas. So PV equals nRT, which means that once you fix the P and V, so let's say you have a point right over here, then you know that T is equal to PV over nR. So given this PV, you can perfectly determine the exact value of the T. So T, or in other words, T is not a free variable. It's not something that you can move around once P and V are fixed. So now we have a PV diagram. This is like a very typical graph, as I said. And what we're going to look at are some special curves that go along it when you have some variable fixed. So for example, if we fix V, this is what we call an isovolumetric process. Then on the graph, very obviously, it's going to look like a vertical line, like this. Now, what can we know about a process like this? So the thing that we use to examine this is the first law of thermodynamics. So let me put this right over here. Delta U is Q minus W. Now, for a process like this, we should note that since the volume doesn't change, work does not change. And we would actually quickly realize that work, in fact, is an integral of P dV. Or in other words, you can just write, if you want it infinitesimally small, you can just write it as P dV. This means that, let's say, if I moved from here to here, I increased the volume. So basically, in this diagram here, the piston would move up, and the gas basically did work on the outside system. And the effect, or what it basically did there, was that it did work. And how much work did it do? It did this much work. You can, in fact, easily derive this from work equals FD. This would translate very nicely into P dV, or basically PV, P change of V. So like if you don't know calculus, dV just basically means change of V, but except that it's infinitesimally small. So actually, I'll just do P delta V. So this is something that we can use to calculate W. Now, returning to this isovolumetric process, we would find that the V does not change. Or in other words, inside of P delta V, this delta V is equal to 0. So work is equal to 0. And that gives us delta U is equal to Q. Right, so this is a conclusion that we can get from an isovolumetric process. Or in other words, if you think about this diagram again, if you fix the piston here, all the work, or like all the effect, the only effect of applying heat to this system is that the internal energy, or the temperature, increases, right? So all of the heat gets contributed to the temperature increase. Right, so that is situation 1. Then another thing that we want to examine is if we have a fixed P. When we have a fixed P, there's really nothing too special. Wait, actually, let me change the color 1 second. If we have a fixed P, we have an isobaric process. And on the graph, it would look something like this, right? There's really not much special about this. We would find that P is constant, which means that no matter where you go, the P is constant. So you can just simply take this integral would immediately simplify into something like this. So like actually here, if we use the non-calculus, we already have what this gives. So we would simply have delta U equals Q minus W. W is just P delta V, where P is fixed. It's a constant. So in either way, if you're given two of these terms, you can figure out the other without much complication because your P is fixed. So this is like a case that's not so exciting, actually. Then the next two are the most important two, I would say. The first being fixed temperature. So once you're being fixed a temperature, you would actually, if you return to the ideal gas law, you would find that PV equals nRT, and that this right-hand side is a constant. Because T is constant, R is constant, and N is also constant. It's a closed system. Now, on the graph, this would just be PV equals a constant, which is basically a hyperbola. So it would look like this. And one nice way you could consider this is that once T is fixed, your point would just move along this like a train. It's like those are like they're fixed paths once T is fixed. And now notice the relationship between this line and this line. So let's say we have this T2 determines this T1 determines this. This T2 is bigger because the PV equals something. This something is greater because it's on the outside. So we would see that the more you move away from the origin, the greater of a temperature you would have. Now, what happens when we fix T though? We see that, let me remind you that U is equal to, U is a unique function of T, as we mentioned right over here, right? So U equals 3 over 2 nkt. So when you change U, so delta U equals delta of 3 over 2 nRT. Now, notice also that basically we already said that this is constant, right? But another way to look at it is that T is constant, and all of these are constant. Basically, it's the same reasoning. So delta U is equal to 0, essentially, right? There is no change in internal energy because the temperature does not change. And this should be equal to Q minus W, which means that Q is equal to W. And so this means that all of the Q, or all of the heat that you put into the system, is contributed to a work done by the gas. So if you put energy into it, if you look at this diagram right over here again, if you heat it, it would push the piston outward without increasing the temperature. And this is what we call an isothermal process. Right. So all the work, all the heat gets contributed to work right over here. So this is an isothermal process. And finally, we have an adiabat. So an adiabat, if you think diabat, basically means that you don't put in any heat. So sorry, not fixed Q. In fact, here it would be Q is equal to 0. So this is an adiabat. Adiabatic process. And this is actually, this basically just means that Q is equal to 0. So immediately we would have delta U is equal to negative W. And in fact, we know through some derivations that we'll cover in another video that the graph of an adiabat on the PV plane can be seen from this equation right over here. So basically, P times V to the 5 over 3 is a constant. So this, in fact, would be more steeper than the isothermals. They would look something like this, and this, and that later will be very important in Carnot engines. So this is an adiabatic process. There's not much to know about this for now, but these are the four main types of thermodynamic processes that we can do to such a system. And knowing these conclusions for each of the different cases is going to enable you to solve all of like high school physics. Now keep watching to get to in the next video entropy, and then in the next video Carnot engines. And then in a separate video though, I'll be doing some derivations about calculating the area under an isothermal process. So like this area, because you have a fixed curve, you can know exactly the integral in a very nice expression. But then also we're going to derive exactly why this equation here is true for adiabats.